Hey, good morning. Let's get started. Yes, welcome back. So this is the fifth lecture. So we're gonna finish this system linearity today, and then hopefully we can finish the last property of the system, which is time variance or invariance property. So let's do a very, very quick review on system linearity. A system is linear if and only if we can write it as IFF if the system satisfies the two properties. Number one, additive property. So I guess before we move ahead, let's make sure our symbols are all defined. Here's your system. We introduced an operator concept in the previous lecture. We use and brackets. So the bracket you can take anything inside the bracket. Input is x of t, y of t is defined as the output. So input, this is just a symbol, right? So you could replace the symbol x of t with x1 of t, x2 of t. So replace it with a specific type of input. Of course, it will generate a specific type of output. So additive property, what it says is, if you give the system with an input of x1 of t plus x2 of t, so this is your input here. Sorry, let me turn on my little highlighter. Okay, so this is your input. And additive property mandates that this should be the equivalent to the addition of the system outputs when the input is separately given as x1 of t, x2 of t. So that's the additive property. The second property is called the homogeneity property, or homogeneous property. So this property says this time you have input c times x of t, and c is a constant. So now your input, right, is this c times x of t. And this input produces an output. And the homogeneous property says this has to be the same as c times mx of t. So these two properties will ensure that the system is a linear. Or the other way around, if the system is linear, then the system will follow the two properties at here. And we also introduced one single property, which is a combination of the additive and the homogeneous property, and which is what we call the superposition property. Right? So alternatively, you can use this so-called superposition property. So this property, as I said, is a combination of the above two properties. So you can see now the writing is like this. Your input is c times x1 plus C2 times C1 times x1 plus C2 times x2. And that should, so now you can see, right? So your input is this whole chunk right here. Right? This is your input. And this will produce an output, right, given certain system operator. And this output needs to be the same as C1 times m x1 of t plus C2 times m x2 of t. So equivalent, you can either use the superposition to check the system linearity, or you check the system linearity using the two properties separately, right? Additive or homogeneous. In most of our assignments or questions, we probably require you to do this separately as an exercise at least at this stage. So once you actually know how to do this, you are able to do this very naturally. So the examples, I will give you actually an example of how to use this one to check the system linearity. Okay. So in the previous lecture, we have demonstrated using additive property and homogeneous property to check system linearity. So I think maybe for now, let's maybe use an example, right? To use this, show an example to use superposition property to check the system linearity. So let's take a look at an example here. Given the following system, another y of t equal to m x of t. So you have input as x of t, you have output y of t, and this is a system represented by the operator m. The system expression is given as this. X t minus 2, and then x of 2 minus t. I know the expression immediately will actually, not going to be interesting to most of us. This is very different from a typical system that you're given, right? Sine t, cosine t, t squared, right? This is just a purely symbol here. And what's even worse is this system here, you can see there's a delay. There's delay either to the left, to the right, right? There's a reflection, okay? So the point here is, of course, we want to check if system is linear. Right. So it doesn't matter how weird the system looks like, and I want you to stick to the principle. Okay? The principle is whether you're using additive property or homogeneous property, or you're using just the superposition property. And I'll show you there are a couple details set here. But some of the details I think I demonstrated more of just how you do the substitution, right? Substitution here. So now in this case, as I said, I'll check the system linearity using the superposition property here. Okay. So we'll use the superposition property. Which means I am going to check this term on the left side. I'm also going to check this term on the right side, and then make sure that these two terms are the same as each other. If I can show that these two terms are the same as each other, then our objective is reached, right? So the system is linear. If I can show that the system is not the same as each other, the two sides, then it's nonlinear. So that's the idea. Okay. All right, so let's do this. first, let's check m. What is m c times x1 over t plus c1 times x1 plus c2 times x2 of t? Okay. All right. So before we move ahead here, sometimes you should bear in mind it might be easier to actually introduce intermittent variable to help you with the situation of the question at it here. Okay, so where is my okay, so I'm going to do this. Okay, I'm going to because when I have the system given at it here, when I have an input at it here, okay, my first instinction is, it's very, especially at the beginning, it's mess. So I don't know what to substitute. So what we can do is, let's introduce an intermediate variable. Let's call it x3 of t. And let's call this x3 of t as c1 x1 of t plus c2 x2 of t. Okay, so let's try this. Okay, so by doing this, remember, this is C1 and the C2, they're constants. So now, instead of a m bracket, this is C1 x1 plus C2 x2. So alternatively now, I'm just checking what's mx3 of t. What's mx3 of t? Of course, x3 is already defined at here, so that's exactly what we're trying to do. Okay, except I'm just introduced this as a intermediate variable. So I'm going to put in the bracket just for your information that this is equivalent to what we're trying to do. Okay. So this is mx3 of t is the same as what we're trying to check. Right? So now, if your input is x3 of t, right? So whatever x3 of t is, then what is the system output? Basically, right, your input is x3 of t. You go back to your system. You go back to your system here, you look at the system. I'm going to replace the current symbol x with x3, although I don't know what x3 is, right? I'll replace x3 at here. And then what is the system output according to the system? You look at the actual system output here. What will be the system output now if this x is x3? What do you do? Or what do you replace? Exactly. So what do you replace? You're replacing all the x that are here with x3, right? So that's pretty straightforward. So x3, t minus 2, then plus x3, 2 minus t. This is straight from the original system. You're not doing anything, making any change at all, right? Okay. So now it's up to me to find out what is x3 t minus 2 and what is x3 2 minus t. Right? So those are two functions basically. Right? Those are two inputs. So what is x3 of this, x3 of this? Then I go back to, let's do it separately. So basically, let's see, what is x3 t minus 2? Okay, yeah. So what is x3 of t? Here's my original definition, x3 of t. Right? It's right here. Okay. So now what's the difference now? See here, this is your x3 of t, and this is x3 of t minus 2. Okay? So basically, let's go backwards a little bit here. Let's make use of maybe a very simple situation. If I tell you x of t is t squared, so then I ask you, what's x of 2? What do? You put the 2 into the t, right? Okay. So whatever the 3, you put a 3 into the t. So what if it's not a number? What if I replace the t with t minus 2? What do? Exactly, you do the same thing, right? You replace the t with t minus 2. So the point essentially here is, if there's a change inside the bracket, and this change inside the bracket means you're changing the original variable t into whatever the new change. So then you do the replacement accordingly. Right? So now my change is I'm changing t into t minus 2. So what is the expression for x3 of t? It's c1x of t and c1x1 plus c2x2. I mean, I don't have a t squared here, but I have a t here, right? So according to the principle I have just iterated, I'm going to try to find all the t and change the t to t minus 2. So this expression here becomes c1 x1 t minus 2 plus c2 x2 t minus 2. So if you really have an expression given for x1 of t, x2 of t, then you could do the specific replacement like this, right? So this is a very abstract replacement, but it's the same meaning though. It's all good, right? So now you can, if I have to write a little bit of here, you try to find the t, try to find a t on the right side and replace it with t minus 2. So that's how you deal with this kind of a expression based on the given expression. Okay, so now I have x3, so then you can try x3 2 minus t. x3 2 minus t. It's equivalent, right? Doesn't matter how complicated the replacement is supposed to be. You go to the right side, you find the corresponding t, then you change that to x1 2 minus t. So now you have the expression for both of the terms that are here. So now I can actually write down m x3 of t equal to, so this term plus this term, right? C1, I mean there's common factors here, so you could just C1 x1 t minus 2 and then plus x1 2 minus t, and then C2 x2 t minus 2 plus x2 2 minus t. Here, this is basically the superposition, the left side of the superposition we're checking. Okay. Any questions so far? Yes. Sorry, the question. Like for the bracket, you just put C1, X1, and inside the bracket, like T minus 2 plus 2 the math is very hard to understand the question here. Can you take out X1 and X2? Can I take out X1 and X2? Put them beside the C1 and C2 outside the bracket. Still trying to understand the question. I think he's treating it. Yeah, I think he's treating it like a variable versus a function. Sorry. Can I take out x? Still quite understand. Why don't you come over here? Maybe the student understand better than me. Yeah. We'll talk about it in the lecture. But okay, if there's somebody says you're trying to multiply x1 into the bracket, No, not like that. Factor out x1. This term here? Tell me if you're coming in. Monday morning, I'm a little slow.
I believe what he's saying
Yeah.
is to write it such as C1, X1, and then you'd have 2 minus T plus, oh no, I wrote it in the wrong spot. Oh, not used to this pen.
Press this and erase that.
Okay.
Yeah, go ahead.
So it would be down here.
Yeah.
So it would be C1, X1, and then in the brackets you'd have T minus 2 plus 2 minus T, and then they're wondering whether the X would just kind of factor in
I
like
see.
that.
I see. Is that what you're saying? Okay. The answer is no. Yeah. So I think I need to re-emphasize this. When you see a symbol like this or symbol like this, right? This doesn't mean it's x times t minus 2. This means it's a function. It's a function x with a variable t minus 2. Okay? So maybe this actually is, t minus 2 squared plus t minus 2 cubed, that kind of thing, right? So this absolutely is not x times t minus 2. So then in this case, right, this doesn't mean that you have a common factor x1 for the two terms, right? So this just means there are two functions here. Both functions are in terms of the variable x, but the variable is different, right? This is the first one is a function of t minus 2. The second one is a function of 2 minus t. Okay. That's actually a very common mistake. I've seen some students do that in the exam, right? They simplify. They can, you got to write basically. You got to write right here, and then they did one more step, which became wrong, right? Is that good? Yeah. Thank you. Okay. That's the left side. So now let's check the right side, right? So the right side is C1m x1 of t plus C2m x2 of t. Okay. So the right side is fairly straightforward. Okay. The right side, mostly you just rewrite whatever the system is, because here you have constant times m x1 of t. Then you say, what is m of x1 of t? So you go back to the system. Here is x. You replace x with x1. And this is your actual system expression. You find all the x's replaced with x1. So now you have your first expression, c1 x1 t minus 2 plus x2 2 minus t. Then plus c2, the second one, same there, x2 t minus 2 and x2. Oh, this is x1. Oh, sorry, x1, yeah. x2 2 minus t. That strictly come out of the original system expression. So then it's time for you. You could rearrange, but I think you already can observe the expression on the right side is the same as the expression you have just obtained on the left side, based on the superposition property. So then you can make a conclusion, right? So you could write one more side here. You can see the left is equal to the right. Hence, system is linear. For that, we're looking expression representing the given system turned out to be a linear system. I use the superposition property out here, but I highly recommend that you check the additive property and homogeneous property applied to this question. Okay? It's an exercise. Yeah. Very similar, but of course you're going to end up with the same conclusion. Any questions so far? Okay, good. Yeah. All right. My intention may be, there are certainly more examples, and I actually have more examples given in the lecture notes. So I highly encourage you to go over the examples. I may actually give you more examples or exercise later when we finish the system properties. So let me maybe start the next topic because I don't want to fall in too far behind. Okay. Any questions so far on this part? Okay. Yes? Oh, the left side is this one, mx3 of t, or mc1x1 plus c2x2. Yeah. Okay, so if there's no question, I wanted to start a new topic. If I have more time, I can probably come back to one more example. But let's start a new topic. And this new topic is the last property regarding system. Basically, we look at the system, whether it's a time invariant or time variant. As the wording, you can clearly see, right? Time variant or time invariant, meaning time is the horizontal axis. And then varying or invariant means there must be something either changing or not changing as time goes on. That's essentially what time varying or time invariant means. Okay. So here's a formal definition. Let's define a system for us. We define this system here. We use the operator m representing a system. We use the inputs, which is x of t. We also use y representing the output. So the definition says the system is time invariant. I'm going to use the Ti for the future. So Ti here representing this is a shortened name for time invariant. If and only if the system time invariant, if and only if all input value x of t, so all of the inputs x of t and says if for all the input x of t and any values at t naught, so it doesn't matter what kind of input is this, it doesn't matter at what time at t naught, right? So you give any value of a constant t naught, then the output, okay, the output of the system corresponding to x of t minus t naught, corresponding to xt minus t naught, is y of t minus t naught. That's the ends of this definition. Okay, so let's read it again and then understand a little bit about what exactly is going on here. Right? So first of all, we all know the current input is x of t. And then we give ourselves a constant t naught. So now we're giving ourselves a new input, x of t minus t naught. So this is a new input. Right? The other input is x of t. But the new input, you look at the new input, this is essentially a shifted version of x of t. So it doesn't matter what x of t is. As long as you write it as x of t minus t naught, you're essentially shifting this x of t, depends on the t naught, shifting this to the right by a distance of t naught. Okay? So, but this is the new input, right? What's my old output? Old input. Old input is x of t, right? Yeah. And old inputs produce y of t. Okay? Now, the new input, according to the definition of time invariant, the new input needs to produce y of t minus t naught. So you can clearly see what is the connection here. Old inputs produce a y of t, and now you're shifting the new inputs by a t naught to the right. If the system is time invariant, then it guarantees that the system output is just a shifted version of the original input, original output. Right? So this is shifted the input, this is the shifted original output. If this is true, according basically what the definition says, then we can conclude that the system is TI. And that's how you interpret this time invariant property. So let me use a graph at here to sort of understand a little more about this time invariant property. Okay, suppose this is your input x of t. So I'll just arbitrarily draw the input signal x of t. Then you feed these inputs into a system. Our system, let's call it the M, operator M. Okay, assume the system is a TI system. Okay, let's assume the system TI. Then the system will produce certain outputs. So I don't know what to say, but basically let's just draw an arbitrary output to represent this idea. So now, then you decide to shift this. You decide to give the system a new input. Let's call it x1 of t. And this new input is a shifted version of your previous input. So you're shifting to the right by t naught. So this t naught here, everything is just shifted to the right by t naught. You give it to the same system, the same TI system. Then, because the system is already, the system time invariant. So technically, you don't even have to do any experiment at all, right? So somebody says, here's just my system. Here is the new input. Can you tell me what the output is? Sometimes you do experiment, you put this new input to the system, you measure on the other end, and you tell him what the system output looks like. Now in this case, because I know this time invariant, then I can immediately tell people, look, your output is actually shifted version of the previous output. That's how you can make use of this time invariant property. So you can also now in your head kind of think about maybe alternative wording for the property. What you could also see is, given a time invariant system, if I delay my input by t naught amount of time, then my output will also be delayed by a corresponding amount of time t naught. So that's, in this case, I'm talking about delay, which is t naught is greater than 0. Okay. So it's equivalent, right? If you see that, that's equivalent to see the time invariant property. Okay. So now, if I have a question and I'm asking you to check this time invariant or time variant property, then let's take a look example. Then your objective, right, is to check two things. So let's say, for example, if I give you a system which is look like this. So here's the system. Y equal to m of x of t equal to t times x of t. The system, if you have to plot it, I mean, if you just draw one single box, so here's your x of t, right? The output is t times x of t. And obviously, what's going on inside the box is probably, your input is x of t, and then you got a t over here feeding into this junction, and then output is t times x of t. Right? So that t is part of the system. So let's check ti or not. So check ti or not, meaning what do you need to check, right? You look at the ti property at here. You want to see, if you want to see that if I delay the input by t naught amount, I want to see if my outputs will actually be the delayed version of the previous outputs. Right? That's what I want to check. So in other words, we need to check if I change my input to t minus t naught, if this term equal y of t minus t naught. That's what we need to check. If the answer is yes, then you have a ti system. Otherwise, it's a time varying system. Okay. So again, don't take it for granted that this is equal, right, from the beginning. You need to find what is the left side, what is the right side, then you compare, you make a conclusion. So let's take a look at, in this case, what is m of x of t minus t naught first. And then we'll look at what is y of t minus t naught. Now, y of t minus t naught is actually quite easy. So often in time is this one will be a little bit tricky, okay, to your brain. So what do we do is, as always, okay, if the input term is a little bit too looks complicated, you could always introduce a new function to represent this new input. So let me introduce a new function name called xd of t equal to x of t minus t naught. Then, if my input is x dt, d of t, xd of t, it's like a delayed input. Okay. So xd that's this term. So basically that's what I'm trying to get, right? So m of xd of t. If my input is xd of t, what would be my output? You go back to your system. Right? This is where, like what we did in the previous case, x now is changed to what? What symbol? xd. So you go to the right side, you try to find all the x's and replace the x with xd. In this case, there is only one x, so t times x d t. And we have x d of t. That's x of t minus t naught. So I'm going to write this as t times x t minus t naught. Right. There we go. So that's the left side of what we're checking, right? So you should know exactly, this is basically m x of t minus t naught. Okay, now let's go to the right side of this expression. So what is y t minus t naught? So I'll give you a chance to write it down here. So here is y, which represents your system output. Yes? Here? You mean it should be xd? No, it's xd is over here. And I define my xd of t as x of t minus t naught, which is this one here. Yeah. It's the same function. It's just I'm writing it a little bit different. So for example, right, let's say if I have x t minus 2 equal to t minus 2 squared. This is a function of t minus 2. And of course, this is equal to t squared minus 4t plus 4. So you could define it as x1, just a single function of t. Right? This is a function of t. It's also a function of t minus 2 if you write it this way. Okay? The difference, right? But in terms of the final result, it's the same thing. Okay, good. So get back to this right side here. Y of t minus t naught. So give you a couple minutes. What is y of t minus t naught? Here's y of t. So first thing, you have to observe what's the difference? And what do I need to replace? The difference is original y of t. Right now is t minus t naught. Anything in the bracket is the variable, right? It's the independent variable. So now you have a t, and t is being changed to t minus t naught. So the rule of thumb is you go to the right side for the expression y of t, which is this, and you look for which variable? You look for what variable? Variable x or variable t? Variable t. And you replace the t with t minus t naught. That's the rule of thumb. There are two t's here. You replace both t with t minus t naught. And of course, I mean physically they're not really the same because this is just a variable here, and this one here, this is a variable part of the function x. Right? Yeah. So that's it. You end up here without giving the actual function x. You don't have to write anymore. So it's time for you to make a comparison of the left side and the right side. Apparently, right, there's difference. This one is t times this. This one is t minus t naught times this. So you can see left not the same as right. I mean, I'm writing left not the same. You could write m of this not equal to y of t minus t naught. Right? So maybe when you present your solution, you should write it more or less like this. If they're not the same, then you can immediately draw a conclusion the system is time-variant. It's time-variant. So that gives you some idea of how you can check the time-variance property, right? By doing similar, it's always kind of substitution, right? Now you have a feeling here. You do the substitution correctly. So let me ask you another quick example here, and see if you can get a feeling. So what if my system is changed to cosine t times x of t? So let's say I have a system of this. Do you think this is a time variant or time invariant system? Anybody? Yes. Time variant, right? Yeah. I mean, the only difference is this is cosine t, and this is t, right? The only difference. But both of you look at this one here, the t and cosine t, both of these, they are time varying quantity, right? And they're not part of the input x. So, and also a similarity between what's seen this one here. So what I could also see is, you can see now the time t, right? The time t actually explicitly shows itself. Okay. It's not embedded within certain function. It's explicitly outside part of this system expression. And that, if that's the case, you can actually make a safely conclusion without even doing the checking. The system is actually time variant. So that's usually the case. So, for example, right? So let's say let me see. What's a good example? Okay. I think when I do the review, is a review, I introduced a system called a mass spring damper system, right? And that system can be described by this second order differential equation. So this is a mass spring damper system. Okay. So in writing it here, this M, this C, and the B here, those are called the system parameter. And F is input, and Y is the X is output. So system parameters, mass, this is K, sorry, this is K here, spring stiffness. MC, the damping ratio, K is the spring stiffness. Right, those are system basic parameter. Parameters associated with the components of the system. Right? You have a total mass, you have spring stiffness, you have a damping ratio associated with the damper. So the parameters set here, right? So the question basic parameters, they could be constant. Constant means the mass never change, the stiffness never change, and the damping ratio never change. But it could also be a non-constant value. So for example, actually a student came to me after that. Can you describe the car's suspension system using this equation? Yes. So car suspension system is another example of a mass spring damper system. Okay. So you do have a spring, right? You also have a damping, and the car's mass is the mass. Okay. So as you are driving a car, so what do you notice when you drive a car for over 10 years or even 20 years? The suspension system becomes what? Sorry, come what? Didn't catch the word. Out of what? Underdamped, right? If I use a more lay word, becoming softer, isn't it, right? Yeah. So basically, if softer means what? Which has changed? Which has changed? Damper or spring, exactly. Yeah. The spring stiffness most often changed. You have to change the suspension system, right? That's an example of time-variance system parameter. So if these parameters are time-variant, then the system here will not be a time-invariant system. And this is still a linear system. Right? We actually have an example in my lecture note to prove this is a linear system. But that's a real-time example of what could be a time-invariant system. Okay? Yeah. I do have one more example, but I think I covered that at the beginning of last lecture. Then we can start a new topic, okay, called convolution. Okay. Any questions? Okay. Yeah, come over here if you have any questions.